Imagine a warehouse at night. It's massive, maybe 100,000 square feet, just packed to the steel girders with stacked wooden pallets.
Right, a total tinderbox.
Exactly. And now imagine a stray spark from, say, a forklift battery charger. Within minutes, the corner of the building is just fully involved. The heat banks up against the ceiling, the smoke detectors trip, and the fire alarm starts shrieking.
Yeah, and this is the exact moment the sprinkler system is supposed to be the hero, right?
Right. The glass bulbs in the sprinkler heads shatter from the heat, the valves open, and instead of a life-saving deluge, you just get a weak, sputtering shower. The water just dribbles out.
Oh, man.
Yeah, the fire spreads, the roof trusses fail, and the building is a total loss.
It's the nightmare scenario for any facility manager. And, the immediate assumption is usually that it was a mechanical failure, like a closed valve or a broken pump or maybe a cracked main.
But so often when the investigators dig into the ashes, they find that the pumps were running perfectly. I mean, the valves were open, the municipal water supply was completely fine.
Really? So the equipment actually worked?
The equipment worked. The failure wasn't mechanical. The failure happened on a piece of paper like 5 years earlier, just sitting on a desk. The failure was mathematical.
Ah, I see where you're going with this.
Yeah, the facility manager decided to change the type of inventory they were storing. So maybe they moved from, unboxed metal parts to high-density plastics, and they stacked those new racks 10 feet higher.
Right, so they changed the fire load.
Exactly. They changed the fire load without recalculating the fluid dynamics required to push enough water through those existing pipes to suppress that specific, much hotter fire.
They basically misunderstood the physics of fluids in motion. I mean, they assumed that just because the pipes were full of water, they had protection. But capacity is not the same as flow.
No, not at all.
And flow is entirely dependent on pressure, friction, and the physical geometry of the system.
Which is exactly why we are jumping into this today. For you, the listener, whether you are, managing that warehouse, designing a laboratory, or most likely staring down the barrel of the ASP exam.
Yes, the Associate Safety Professional certification. It's a big one.
It is. And today we are looking squarely at Domain 1, Topic 3. This is the realm of calculating flow rates for ventilation, hydraulic, and pneumatic systems. And man, we have a formidable stack of source materials today.
You really do.
We've got the ASP blueprint, the BCSP exam prep problems, my safety prep guides, and a whole arsenal of industrial hygiene formulas sitting on the desk here.
It is an incredibly dense stack of material, honestly. To the uninitiated, it just looks like alphabet soup. You've got endless variables, Greek letters, exponents, and constants that, frankly, seem pulled out of thin air.
Yeah, and rote memorization is absolutely the enemy here. If you just try to, flashcard these formulas, the exam writers will trap you.
Oh, they definitely will. They know exactly how to twist the variables to expose a lack of fundamental understanding.
So our mission today is to pull these equations off the page and drag them into the physical world. Okay, let's unpack this. We're going to look at the actual microscopic behavior of air molecules bouncing around inside a metal duct and, the crushing weight of water sitting in a municipal tower.
We really need to start by defining our terms, though, specifically the concept of a fluid. Because in everyday conversation, people use the word fluid interchangeably with liquid.
Right, like drinking your fluids.
Exactly. But in physics, and certainly on this exam, a fluid is any substance that continually deforms or flows under an applied shear stress. That means both water and air are fluids.
Okay, so the math is essentially the same for both.
Yes. The math we use to move water through a fire hose shares a tremendous amount of DNA with the math we use to pull toxic welding fumes through a sheet metal exhaust duct.
The primary difference being compressibility, right? Like, we can squish air into a scuba tank, but we can't really squish water.
That's the main difference, yes. But here's the trick. For standard industrial ventilation, just running a fan to clear a room, the pressure changes are so relatively small that we actually treat the air as if it were incompressible.
Wait, really? We just pretend it's like water?
Essentially, yes. We assume the density remains constant for those basic calculations, and that assumption is the bedrock that allows us to use the single most important mathematical relationship in this entire domain.
The continuity equation,
Yeah.
Looking at the source materials, everything seems to radiate outward from this one anchor point. Q equals V times A.
Yes, volumetric flow rate equals velocity multiplied by area. If you take absolutely nothing else away from your study sessions, this relationship is the key.
It's the master key.
It is. It represents the conservation of mass. So if we have a closed system like a pipe or a duct, and we are treating the fluid as incompressible, then whatever volume of fluid enters one end must exit the other end in the exact same amount of time.
Right. You cannot create or destroy mass inside the pipe. It has to go somewhere.
Exactly. So let's physicalize these variables. Q is the volumetric flow rate. It's the sheer amount of stuff moving past a fixed point.
So if I'm standing next to a transparent glass pipe with a stopwatch, Q is how many gallons of water or how many cubic feet of air rushed past my shoes in exactly 1 minute.
You've got it. In hydraulics, dealing with liquids, Q is almost universally expressed in gallons per minute, or GPM. In pneumatics and ventilation, dealing with air, it's cubic feet per minute, or CFM.
Okay, and then we have V, which is velocity, so speed. How fast are the individual molecules actually moving down the line?
Right, and we measure this in feet per minute, or FPM.
And finally, A is the cross-sectional area. So if you take a saw and cut the pipe perfectly in half and look straight down the barrel, A is the surface area of that circle.
Yes, and this introduces the very first trap you will see on the exam. Area in this equation must be in square feet.
Which is sneaky because nobody measures ductwork or piping in feet. If I go to a hardware store, I'm buying an 8-inch duct or a 2-inch PVC pipe. The real-world input is always in inches.
The exam writers rely completely on that real-world habit. They will give you a problem featuring an 8-inch diameter duct and an air velocity of, say, 1,000 feet per minute, and ask for the total flow, Q.
And if you just calculate the area of an 8-inch circle and plug that directly into the formula,
your answer will be wildly incorrect because you are multiplying inches by feet. You must convert those inches into feet before you find the area, or convert the square inches into square feet afterward. The units have to align perfectly.
Right, apples to apples. Okay, so let's look at how these three variables interact when the physical environment changes. The continuity equation expands to say Q equals V1 times A1, which also equals V2 times A2.
Meaning the total volume of air, Q, stays locked in. It's a constant throughout the system.
Think about the physical reality of a ventilation system spanning a factory floor. A large main duct runs down the center of the ceiling. It might be, 3 feet wide, but then it branches off into smaller and smaller ducts to feed individual workstations.
Exactly. The geometry is constantly changing.
I always picture a multi-lane highway. So you have a massive 4-lane interstate. That's our large area, A1. Let's say we have a steady flow of 1,000 cars passing a mile marker every single hour.
Okay, so that's our Q, 1,000 cars per hour.
Right. And because they have 4 lanes to spread out in, they can maintain a comfortable, moderate speed. That moderate speed is our V1. But suddenly, the highway enters a mountain pass, and those 4 lanes pinch down into a narrow 2-lane tunnel.
So the area of our road, A2, just got cut in half.
Exactly. But the cars haven't disappeared.
Right, the system is closed. Those 1,000 cars per hour still have to get to the other side. Q cannot change.
So if the physical space to move through is suddenly cut in half, the only possible physical response is for the cars to drive twice as fast.
As area goes down, velocity must go up proportionally to maintain the constant Q.
And the reverse holds true, right? When the cars exit the tunnel and the road opens back up into a massive superhighway, the area increases dramatically.
The cars spread out, the velocity drops, but that 1,000 cars per hour metric remains absolutely stable.
Now, conceptually, that seesaw relationship is pretty intuitive. Area goes down, speed goes up. But sitting in a sterile testing center with a countdown clock ticking in the corner, algebra anxiety is very real.
It really is. People panic.
You have Q equals V times A, but the question gives you Q and V and asks for A, or it gives you Q and A and asks for V. How do we quickly manipulate this on the exam?
The sources reference visual transposition tools, like a triangle or a pie chart, but really it comes down to understanding the relationship. Q is the heavy hitter. It's the product.
The big number on top.
Right. If you need to isolate one of the components, either velocity or area, you always take the total volume and divide it by the piece you have.
Like breaking down a total budget. If my total budget is Q, and I know the cost per item is V, I divide the budget by the cost to find out how many items A I can buy.
That's a great way to think about it. Let's run the exact scenario from the reference guide. The problem states you have a measured total volumetric airflow, Q, of 3,225 centimeter.
Okay, 3,225.
And you have an anemometer reading showing an air velocity, V, of 350 ppm.
Yeah.
The question asks for the required cross-sectional area of the duct.
So I need the area. I take the total Q and divide by what I know. V area equals Q divided by V.
Yeah.
So 3,225 divided by 350.
Exactly.
That comes out to roughly 9.21. And because my flow is in cubic feet and my speed is in feet, my area inherently lands in square feet, 9.21 square feet.
It's a very clean mathematical operation, but it begs a larger question about the physics of the system. We know how to measure the volume, the area, and the speed. We understand how they react to each other, but air does not spontaneously begin flowing through a duct simply because the duct exists.
Right, something has to push it or pull it. The air in a room is perfectly content to just sit still until a force acts upon it.
Which requires us to leave the geometry of the duct and enter the thermodynamics of the system. We have to talk about pressure.
The pressure trinity. This is where the source material gets really dense with definitions. The core equation here is TP equals SP plus VP. Total pressure equals static pressure plus velocity pressure.
Yes, that's the one.
Let's break this down to the molecular level.
Yeah.
What is actually happening inside a metal duct when a huge fan turns on?
Think of pressure as the transfer of kinetic energy from gas molecules bouncing against a surface. In an industrial ventilation system, the prime mover, usually a large centrifugal fan, imparts massive amounts of energy into the air.
Okay.
This total energy budget of the airstream is what we call total pressure, or TP.
It's the entire bank account of energy available to get the work done.
Exactly. And that energy manifests in two distinct ways. The first is static pressure, or SP. This is the pressure exerted by the fluid in all directions simultaneously, regardless of whether the air is moving down the pipe or just sitting completely still.
I always try to visualize this with an inflated rubber balloon. You tie the end off. The air inside isn't flowing anywhere, but the molecules are still violently vibrating and bouncing off the inner walls of the rubber, stretching it outward.
Right, they're constantly pushing against the boundary.
That outward push is pure static pressure. In a duct, it's the force constantly trying to boost the sheet metal seams apart.
Or if the fan is located at the far end of the system, pulling air through the duct like in a negative pressure system, the static pressure is the force trying to suck the walls of the duct inward. It's trying to collapse the pipe like a crushed soda can.
So static pressure is structural. It's the bursting or collapsing force. What about velocity pressure, VP?
Velocity pressure is the kinetic energy of the forward motion. If you untie that balloon and let it go, the air doesn't just push against the rubber anymore, it violently escapes.
Yeah, it shoots across the rim.
And if you put your hand in front of the nozzle, you feel the wind physically hitting your skin. That directional force, the energy of the mass of air moving in a specific vector, is the velocity pressure.
And the total pressure, the entire energy budget provided by the fan, is constantly being split between these two forces. TP equals SP plus VP.
The relationship between these pressures isn't just theoretical either. It is the ultimate diagnostic tool for a safety professional in the field.
How so?
Well, a vast factory might have a mile of interconnected ductwork hidden above a drop ceiling. If a worker on the floor complains that their chemical exhaust hood isn't pulling away fumes, you can't just climb up and visually inspect the inside of a mile of sheet metal.
No, you'd have to dismantle the entire factory to do that.
Right. Instead, you use the physics of pressure. As air travels down a duct, it encounters resistance, friction against the metal walls, turbulence as it bends around a 90-degree elbow joint, and most importantly, resistance as it gets forced through a filter bank.
And every time the air fights through that resistance, it has to spend some of its energy.
It pays a toll, and that toll is paid directly out of the total pressure budget. If you take a pressure reading in the duct just before a massive HEPA filter and another reading immediately after the filter, you will see a drop in pressure.
Because the air on the far side has less energy, it's spent some pushing through the filter media.
Exactly. And if that pressure drop suddenly spikes, like if the difference between the before and after readings doubles over the course of a month,
then the physics are telling you exactly what is happening inside the invisible system. The filter is becoming clogged with particulate matter. It's offering more resistance, so the air has to spend more energy to get through.
without ever laying eyes on the actual filter, you know it needs to be replaced.
That is so cool.
Yeah.
But how do we actually capture these readings? The sources spend a lot of time on a device called a pitot tube. How does a literal piece of metal measure a bouncing molecule?
A standard pitot tube is an ingenious piece of engineering. It's essentially an L-shaped instrument, a tube within a tube. You drill a small hole in the side of the duct and insert the pitot tube so that the tip points directly into the oncoming wind of the airstream.
Like pointing a weather vane directly into a storm.
Exactly like that. The inner tube has an opening right at the very tip, facing the wind head-on. The air comes rushing down the duct and rams violently into this opening.
So it's taking a direct hit.
It captures the static pressure, the baseline bouncing of the molecules, but it also captures the sheer kinetic impact of the forward motion. So that center tube measures the total pressure.
It takes the full brunt of the system's energy.
Yeah.
Okay, so what about the outer tube?
Meanwhile, the outer tube is sealed at the tip, but it has tiny little holes drilled along its sides, perfectly perpendicular to the airflow.
Oh, I see.
Because these holes face sideways, the rushing wind doesn't ram into them, it just glides past. The only pressure that manages to enter those side holes is the outward bursting force of the air against the walls.
The static pressure.
Yes, the static pressure. So now you have two physical measurements. You pipe those two readings from the pipe tube into an instrument called a manometer.
Let's talk about manometers, because the source material measures all this pressure in a unit called inches of water gauge. And for someone studying for the ASP, they know they need to select inches of water gauge on a multiple choice question.
Right, it's the standard unit.
But what does that physically look and feel like? It sounds completely abstract to me. How do inches measure pressure?
To understand inches of water gauge, we really have to look at the simplest, oldest form of a manometer, the U-tube.
The letter U.
Yeah. Imagine taking a clear piece of flexible plastic tubing, maybe 3 feet long. You bend it into a U shape and staple it to a wooden board. Then you pour a little bit of water into the tube so it settles in the bottom of the U.
Okay, I'm picturing that.
Because the atmospheric pressure pushing down on both open ends of the tube is equal, the water level rests perfectly evenly on both the left and right sides.
You draw a line on the board right where the water sits. That's your zero mark.
Exactly. Now, take a rubber hose from the total pressure port of your pitot tube and connect it to the left side of your U-tube. The pressurized air from inside the duct pushes down on the water on the left side, forcing it deeper into the tube.
And because water is incompressible, as the left side goes down, the right side is forced up.
Yes. The air is physically lifting the weight of the water against the downward pull of gravity. You literally take a ruler and measure the difference in height between the water level on the left and the water level on the right.
Oh, wow. So if the pressure from the duct was strong enough to push the water so that there is exactly a 1-inch difference in height between the two columns,
Yeah.
you have a pressure of 1 inch of water gauge.
That's it. That brings it completely into reality. It's not an abstract mathematical constant. It is the physical strength required to lift a 1-inch column of liquid water.
And in industrial ventilation, we are dealing with incredibly low pressures compared to things like compressed air tanks, right?
Very low. A typical ventilation duct might only have a static pressure of 2 or 3 inches of water gauge. It's a very delicate balancing act.
Okay, so the pitot tube gathers the total pressure and the static pressure. The manometer measures them by displacing water. But the piece of the puzzle we really need to figure out how much fresh air is hitting a worker's face is the velocity pressure, the speed.
Which is simple arithmetic. Since TP equals SP plus VP, we just rearrange it. Velocity pressure is the total pressure minus the static pressure. The digital instrument does this subtraction automatically nowadays.
And once we isolate that velocity pressure, the source materials introduce what I honestly think is the most fascinating mathematical shortcut in the entire ASP curriculum.
You're talking about the 4005 constant.
Yes, we have a formula to instantly translate that tiny pressure measurement from the manometer into the actual speed of the air. V equals 4005 multiplied by the square root of the velocity pressure.
That number 4005 is arguably the most heavily tested constant in ventilation engineering.
But it doesn't just exist by magic, right?
No, not at all. To understand why we trust it, you have to look back to the 1700s, to a Swiss mathematician named Daniel Bernoulli.
Bernoulli's principle. This is the same physics that explain how airplane wings generate lift, isn't it?
Exactly the same. Bernoulli proved that for an incompressible fluid, an increase in the speed of the fluid occurs simultaneously with a decrease in pressure or a decrease in the fluid's potential energy.
So you can trade pressure for speed and speed for pressure. The total mechanical energy remains constant.
Yes. So Bernoulli's foundational equation relates the pressure of the fluid to its velocity and its density. But Bernoulli's original equation is incredibly cumbersome.
How so?
It requires you to know the exact density of the specific fluid you are measuring at that exact moment. And the density of air changes constantly based on the temperature of the room and the barometric pressure of the atmosphere.
Right. And an industrial hygienist climbing a ladder in a dusty factory in, 1950 didn't have a computer in their pocket to calculate real-time air density shifts. They needed a reliable field shortcut.
Exactly. So they standardized the air. They created a baseline called standard air. Standard air is rigidly defined as having a density of exactly 0.075 pounds per cubic foot.
Okay, 0.075.
And this specific density occurs when the air is exactly 70 degrees Fahrenheit at sea level with a barometric pressure of 29.92 inches of mercury.
Basically, a perfectly comfortable spring day on the coast.
Yep. When you take that specific density of 0.075 and plug it into Bernoulli's complex equation, along with the conversion factors to change feet to inches of water, all the messy math collapses. It crystallizes into a single elegant constant, 4,005.
So if I read a velocity pressure of 0.25 inches of water on my gauge, I don't need a physics degree. I just take the square root of 0.25, which is 0.5. I multiply 0.5 by 4,005, and I instantly know the air is moving at 2,002.5 feet per minute.
It's brilliant. It saves so much time.
But there is a massive red flag in the source material about over-relying on this shortcut.
Because 4005 is built entirely on the assumption of standard air. If you alter the physical environment so drastically that the density of the air changes, the 4005 constant breaks down, it lies to you.
Give me a scenario where a safety professional would get burned by this on the job. Let's make it concrete.
Sure. Let's say you were hired to design an exhaust system for an industrial oven. The air inside that exhaust duct isn't 70 degrees Fahrenheit, it's 350 degrees.
Okay, that's way hotter.
As air heats up, the molecules gain energy and spread further apart. The air expands, so the density plummets far below 0.075 pounds per cubic foot.
It becomes much lighter.
Right. Or imagine you are working at a mining facility high in the Rocky Mountains outside Denver. The altitude is 8,000 feet above sea level. The atmospheric pressure is significantly lower than standard. The air is naturally thin.
Again, the density is nowhere near standard.
In either of those cases, high heat or high altitude, if you blindly plug your pitot tube reading into the V equals 4005 times the square root of VP equation, you will calculate an air velocity that is completely wrong.
Because the formula thinks the air is heavier than it actually is.
Yes. You will think you are pulling enough air to keep the worker safe, but because the air is so thin and light, you aren't actually moving enough physical mass of oxygen or exhaust. You have to step away from the shortcut and manually calculate a density correction factor to adjust the math.
That is a critical distinction for the exam. Know the constant, but know its boundaries. All right, so we've mastered the mechanics inside the metal pipe. We know how the volume, speed, and pressure interact.
Yes, the fundamentals.
But the ultimate goal of the ASP isn't just to move air from point A to point B, it's to keep the human being standing in the room from suffocating or being poisoned. We need to transition from the physics of the duct to the toxicology of the workspace.
We need to explore dilution ventilation.
The classic maxim in industrial hygiene. The solution to pollution is dilution. If we have a toxic gas building up in a room, the simplest approach is just to pump massive amounts of clean, fresh outside air into the space until the concentration of the toxin drops below a hazardous level.
It is the most common form of ventilation in the world. Every office building, hospital, and school relies on it to manage carbon dioxide from human respiration.
Makes sense.
The most basic way we measure this is a metric called air changes per hour, or ACH. The formula provided in the study guides is N equals 60 times Q divided by V room.
Let me break that down. Ending the number of complete air changes in 1 hour. Q is our required volumetric flow rate from the HVAC system in CFM. And V room is the physical volume of the room itself in cubic feet.
Right. And the 60 is just a time conversion to bridge minutes to hours.
Let's apply it. Imagine a chemical storage room in a pharmaceutical plant. The room is 20 feet wide, 20 feet long, with a 10-foot ceiling.
Okay, so 20 times 20 is 400 times 10. The total volume of the room, V room, is 4,000 cubic feet.
And let's say the safety regulations dictate that to prevent the buildup of volatile fumes from, microscopic leaks in the chemical drums, this specific room requires 6 complete air changes per hour.
So we need to pull out 4,000 cubic feet of old air and pump in 4,000 cubic feet of fresh air 6 times every 60 minutes.
Exactly. So we arrange the formula to solve for the fan size we need to buy, which is Q. The formula becomes Q equals N times V room, all divided by 60.
We multiply 6 air changes by the 4,000 cubic foot volume, giving us 24,000.
And we divide 24,000 by 60 minutes.
Which gives us 400. So we need an HVAC system capable of delivering exactly 400 cubic feet per minute of continuous fresh air to hit that regulatory target.
It is an essential foundational calculation, but it is a blunt instrument. ACH is fantastic for generalized spaces, but what happens when you aren't dealing with microscopic slow leaks?
That's where things get dangerous.
Right. What happens when you have an open vat of a highly toxic solvent and you know exactly what the chemical is and exactly how fast it is evaporating into the room?
In that scenario, a generic rule like 6 air changes an hour isn't based on the actual physics of the threat. For that, the source materials unleash what I consider the most intimidating equation in this entire domain.
I call it the beast equation.
The complex formula for dilution ventilation, it looks terrifying on the page. Ready?
Lay it on me.
Q equals, in the numerator, 403 times 10 to the 6th times SG times ER times K. All of that is divided by the denominator, which is MW times C.
If I'm sitting in the exam room and that pops up, the instinct is definitely to panic. But if we break it down conceptually, it's actually a brilliant piece of modeling.
It really is.
I look at this fraction as a battle between two forces. The entire top of the fraction in the numerator is the hazard generator. It calculates exactly how much poison is entering the air, and the entire bottom of the fraction, the denominator, is the safety threshold. It defined the regulatory line we cannot cross.
That is an excellent framework to use. Let's analyze the hazard generator on top. We start with the constant 403 times 10 to the 6th, which is 403 million.
Which seems absurdly large.
It is entirely administrative. It's a massive conversion factor that handles the messy translation between pints of liquid, cubic feet of gas, room temperature expansion constants, and parts per million. It just does all the dimensional heavy lifting so we can plug in raw field data.
Okay, that makes sense. Then we multiply that constant by SG.
Specific gravity. This is the density of the liquid chemical compared to the density of water. It tells us how much raw mass is actually sitting in the vat.
Got it. And we multiply that by ER.
Evaporation rate, measured in pints per minute. If a worker leaves the lid off a 50-gallon drum of industrial degreaser, the ER measures how violently that liquid is boiling off into a gas at room temperature. How many pints of liquid physically disappear into the air every 60 seconds?
So the higher the specific gravity and the higher the evaporation rate, the more massive the hazard being generated, which means the top of our fraction gets larger.
Right.
This directly drives up Q, meaning we will need a much bigger fan to handle the threat. That makes logical sense. But then we hit the final variable in the numerator, K, the design distribution constant, ranging from 1 to 10. The sources heavily emphasize this. What is K doing to our math?
K is the collision point between idealized mathematics and the chaotic reality of fluid dynamics. It accounts for incomplete mixing.
Explain the assumption of perfect mixing first, just so we have a baseline.
When you calculate basic air changes per hour, the math assumes that the millisecond a cubic foot of fresh air enters a room from the ceiling vent, it perfectly, instantly, and uniformly disperses into the contaminated air.
Like a drop of blue food coloring hitting a glass of water and instantly turning the whole glass a pale, even blue.
Exactly. But air doesn't behave like food coloring in water. Not at all. Air currents are incredibly complex and chaotic. If the supply vent is on the ceiling and the exhaust vent is on the opposite wall near the ceiling, the fresh air might shoot out of the vent, race straight across the ceiling, and get sucked right out of the room without ever traveling down to the floor where the people are.
We call that short-circuiting.
It's a massive failure of the system. Or consider a room with large machinery. The airflow will hit a machine and bounce off, creating stagnate dead zones behind the equipment where the air barely moves at all.
Oh, that sounds bad.
It is. If a worker is standing in one of those dead zones over an open bucket of solvent, the toxic vapors will just hang there in an invisible cloud, accumulating rapidly, even if the room technically has an HVAC system pushing thousands of CFM.
So the worker breathes in a lethal dose, despite the math saying the room is safe.
Precisely, because the mixing was incomplete. So industrial hygienists developed the K-factor as a safety multiplier. It ranges from 1 to 10.
Okay, so how do we pick a number?
A K-factor of 1 assumes perfect magical mixing, which we never use in the real world. If the airflow design is decent, we might use a K-factor of 3. If the room is cluttered, the ventilation is poor, or the chemical is extraordinarily toxic, we might use a K-factor of 8 or 10.
meaning we look at the theoretical amount of fresh air needed, and we literally multiply it by 10 to guarantee that even the stagnant dead zones eventually get flushed out by the sheer, overwhelming volume of air being forced through the space.
It is brute force engineering to overcome chaotic physics. So that entire top half of the equation calculates the volume of the hazard multiplied by the chaos of the room. Now, look at the safety threshold on the bottom of the fraction, MW times C.
Right, MW is molecular weight, how heavy the gas molecules are, which impacts how they behave when they expand. But C is the critical variable here, isn't it?
C is the allowable concentration limit of the gas in the room, expressed in parts per million, or ppm. This is the regulatory hardline. This is typically the TLV, the threshold limit value, or the PEL, the permissible exposure limit. If the PEL for our solvent is 50 ppm, then C is 50.
So the mechanics of the Beast equation are actually beautiful when you lay it out like that. You take the total amount of toxic vapor being generated every minute, factor in how badly the room mixes air, and then divide all of that by the legal limit of toxicity.
Exactly.
The resulting number, Q, is the exact size of the fan in cubic feet per minute required to hold the concentration safely below that legal limit.
It is a stunning piece of applied mathematics. But just like the 4005 constant we talked about earlier, there is a massive conceptual trap hidden within these calculations that the exam writers love to exploit. It relates back to the standard conditions of the air.
The STP trap. Standard temperature and pressure. Here's where it gets really interesting.
When we discussed the 4005 constant for the physical movement of air through a fan, we defined standard air as 70 degrees Fahrenheit and 1 atmosphere of pressure. That is the universal standard for ventilation engineering.
But when you start calculating the expansion of toxic chemical gases using molecular weight and evaporation rates, you are no longer strictly in the realm of ventilation engineering. You have crossed over into chemistry and industrial hygiene sampling.
And those scientific disciplines have completely different definitions for standard conditions.
They do.
Yes. In general chemistry and the physical sciences, standard temperature and pressure, STP, is defined as 0 degrees Celsius, which is 32 degrees Fahrenheit. It's freezing.
And to make it worse, in this specific field of industrial hygiene sampling, like calibrating the little air pumps workers wear on their lapels to measure vapor exposure, STP is defined as 25 degrees Celsius, which is 77 degrees Fahrenheit.
This creates a diabolical situation for the test taker. You have 3 different baseline temperatures: 70 degrees for fans, 32 degrees for pure chemistry, and 77 degrees for IH sampling.
That is so confusing.
When a question asks you to apply a density correction factor because the environment isn't standard, you have to read the context of the question to figure out which standard you are deviating from.
So if the question is about sizing a centrifugal fan, your baseline is 70. If the question is about interpreting data from a lapel monitor, your baseline is 77.
Right. And if you use the wrong baseline, your volume calculations will be off by a few percentage points due to thermal expansion. And trust me, the BCSP exam writers will absolutely have your incorrect answer waiting as option B on the multiple choice list.
Wow. You must let the context dictate the math. All right, so we've modeled how to flood a room with clean air to dilute a hazard. But as we established with the K factor, dilution has severe limits.
Very severe.
If a worker drops a heavy wrench into a heated vat of trichloroethylene, pumping fresh air into the ceiling vent doesn't stop the worker from inhaling the vapor rising right into their face. Pumping air into the room might actually just stir the toxic vapor around faster.
Dilution ventilation is for managing general low-level fugitive emissions. When you have a point source hazard, a highly toxic, highly concentrated operation like a welding station, a grinding wheel, or an open chemical dip tank dilution is wildly inadequate.
It is dangerous to rely on it.
You cannot let the contaminant mix into the room air. You must physically reach out and grab the vapor before it ever breaches the worker's breathing zone.
Which transitions us from dilution to local exhaust ventilation, or LEV. Instead of a fan blowing air into a room, we are designing a vacuum to suck air out of a specific spot. We are building a hood.
The foundational formula for determining how much suction we need for a plain, open-ended hood is V equals Q divided by, in parentheses, 10 times x squared plus A.
Let's map the variables. V is our capture velocity. This is the wind speed we need to generate at the exact spot where the hazard is originating to successfully pull the fumes back into the hood. Q is the total volumetric flow rate running through our ductwork. A is the cross-sectional area of the hood opening itself. And X, well, X is the villain of this equation.
X is the centerline distance, measured outward in feet. from the face of the hood to the point of contaminant generation.
I picture a standard shop vacuum here. If I spill a pile of sawdust on my workbench, and I take the vacuum hose and press it directly onto the pile so the distance, x is 0, the suction is incredible. It inhales the sawdust instantly.
Oh yeah, maximum capture.
But if I pull the hose back just 5 or 6 inches, the suction seems to vanish. The sawdust barely flinches. The drop-off in power isn't gradual. It feels like it falls off a cliff. Why does distance destroy suction so completely?
It's not just a drop-off, it's an exponential collapse. Look closely at the denominator of the equation, 10 times x squared. The distance isn't just a linear factor, it is squared.
Okay.
This formula is a manifestation of the inverse square law, a fundamental principle of physics that dictates how energy propagates through three-dimensional space.
We see this with light and radiation too, don't we? As you move away from a light bulb, it doesn't just get a little dimmer, it gets exponentially darker.
Exactly. When a fan creates a vacuum at the opening of a hood, that suction doesn't just pull in a straight, laser-like line. It pulls air from all available directions simultaneously, top, bottom, left, right, and front. The suction creates a sphere of influence, an invisible bubble of low pressure expanding outward into the room.
And as that bubble expands, the surface area of the sphere increases exponentially.
The geometry of a sphere dictates that if you double the radius, the distance x the surface area of the sphere doesn't double, it quadruples. Therefore, the suction energy of the fan has to be stretched and smeared across 4 times as much physical space. The velocity collapses.
Let's put hard numbers to this, because the implications for designing a factory are staggering. Imagine a workstation where a welder is fabricating a steel pipe. The fumes are toxic. We install a ventilation hood 1 foot away from the welding arc. So x equals 1.
Okay, x equals 1.
Based on the math, we calculate that we need a specific fan running a specific Q to generate enough capture velocity at that 1 foot mark. But the welder complains that the hood is in their way. They physically move their workpiece just 1 foot further back. The distance is now 2 feet.
They haven't just doubled the demand on the system. Because the distance is squared, 2 squared is 4, the required volume of air Q to reach out and grab those fumes with the same velocity is now 4 times greater.
If they move 3 feet away, 3 squared is 9. We need 9 times the airflow.
And to upgrade a fan to move 9 times more air requires massive industrial-scale infrastructure. The physical size of the ductwork would have to increase exponentially. The electrical cost to run a motor large enough to pull that much air would bankrupt the facility.
You cannot solve distance with horsepower.
No, you can't.
So how do safety engineers actually fight the inverse square law?
By fundamentally altering the geometry of the suction. The equation V equals Q over 10x squared plus A assumes a plain, open-ended pipe hanging in the middle of a room, pulling air from 360 degrees. To improve efficiency, we add physical barriers to block the air from coming from directions we don't care about.
We add flanges.
Yes. A flange is just a flat collar of metal surrounding the hood opening. By putting a physical wall around the opening, we prevent the fan from sucking clean air from behind the hood. We force all the suction energy to focus forward, toward the hazard.
Oh, that makes sense.
A flanged hood changes the math entirely. It drops the 10 in the denominator to a 5, making the system vastly more efficient. And if we can place the hood on a workbench using the table itself as another physical barrier, we cut out even more wasted suction.
The ultimate goal is to enclose the hazard entirely, right? Like a fume hood in a chemistry lab has glass on 3 sides and a sliding sash on the front. You limit the open area so aggressively that the velocity through the remaining opening is incredibly strong.
But even with flanges and baffles, the physics of pulling air through open space are working against you. The source material notes a hard physical limit to Delavalle's equation for capture velocity.
Right, the 1.5 diameter rule.
The formula only works reliably up to a distance of 1.5 times the diameter of a round duct, or 1.5 times the side length of a rectangular hood. Beyond that distance, the math falls apart.
Because the suction is so incredibly weak at that point.
It's so weak that the ambient chaos of the room takes over. Someone walking past the workstation creates a wake of air. The heat from a nearby machine creates a thermal updraft. A door opens down the hall, creating a crossdraft.
Basically any tiny breeze.
Any of these tiny ambient air currents will completely overpower the delicate suction of the hood. The hood becomes functionally blind to the contaminant. The toxic fume will just drift away on a crossdraft before the hood even registers it.
It paints such a vivid picture of how fragile fluid dynamics can be in an industrial setting. Air is a fluid, And it behaves exactly like a fluid, constantly finding the path of least resistance, dissipating its energy rapidly in open space. But for the entire first half of this deep dive, we've been talking about a fluid that is invisible to the naked eye.
Right, gas.
We've modeled its velocity, pressured it through manometers, and calculated its chaotic mixing. Now, I want to pivot. Let's leave the world of invisible gases and look at the physics of a fluid we can actually see and hold in our hands. Let's talk about liquids. Let's talk about hydraulics.
It's a fascinating shift because the fundamental laws of conservation of mass and pressure relationships remain entirely intact. But the immense increase in the physical density of the medium changes the scale of the math completely.
First, we need to distinguish between two fields of study heavily featured in the source materials: hydrostatics versus hydraulics.
It is the classic division between potential energy and kinetic energy. Hydrostatics is the physics of liquids at rest. The fluid is static. It is not flowing through a pipe. It is sitting in a sealed container, exerting pressure against the walls, purely due to the force of gravity pulling down on its mass.
Hydraulics, on the other hand, is the physics of liquids in motion. What happens to the pressure and the friction when that liquid starts moving through a complex system of pipes, valves, elbows, and nozzles?
Hydrostatics is the municipal water tower looming over a town. Hydraulics is the high-pressure water rushing out of the fire hose connected to the hydrant below.
Let's start with the potential energy, hydrostatics. The foundational equation provided for determining the pressure of standing water is beautifully simple compared to the beast equation we just wrestled with. It is P equals 0.433 times H.
This is the formula for calculating head pressure. Let's define the variables. P is the resulting pressure at the bottom of the container, measured in pounds per square inch, or CSI. H is the total vertical height of the fluid column, measured in feet.
And the 0.433 is our constant multiplier. Unlike the 4,005 constant, which required standard error assumptions in Bernoulli's equation to derive, this constant feels much more tangible. Where does 0.433 actually come from?
It is derived directly from the physical weight of fresh water. If you build a glass box that is exactly 1 foot long, 1 foot wide, and 1 foot tall, a perfect cubic foot, and you fill it to the brim with fresh water, that block of water weighs exactly 62.4 pounds.
Okay, 62.4 pounds.
Now look at the bottom of that glass box. The floor of the box is 1 square foot, which means it is 12 inches by 12 inches. If you multiply 12 by 12, you get 144 square inches.
So that 62.4 pounds of physical water weight is sitting on top of an area of 144 square inches.
If we want to know the pressure on just one single square inch, we divide the total weight by the total area. 62.4 divided by 144 equals 0.433.
Wow, it's just dividing weight by surface area.
Precisely. It means that every time you add 1 vertical foot of water height, you're adding exactly 0.433 pounds of pressure to every single square inch at the bottom.
Let's visualize this with the water tower example. A town builds a water tower, and the tank itself sits 10 feet off the ground. What is the static pressure at the valve on the ground level? We take our formula, P equals 0.433 times H. The height is 10 feet. 0.433 multiplied by 10 is 4.33 psi.
Which is practically nothing. The water would barely dribble out of a shower head at 4.3 psi.
So they build the tower 100 feet tall instead. Multiply 0.433 by 100 and you get 43.3 psi. That is standard, highly functional municipal water pressure. But here's the part of hydrostatics that always bends the mind. And it is a concept the ASP exam tests rigorously to see if you actually understand the physics. The formula P equals 0.433 times H only has one input variable.
Okay, it completely ignores volume.
It ignores width. It ignores the shape of the tank. Let me challenge this, because intuitively it feels wrong. Imagine I take a standard 1-inch PVC pipe and I stand it straight up in the air until it's 100 feet tall. I fill it with water. The formula says the pressure at the bottom cap is 43.3 psi.
That is correct.
Now, imagine a massive natural lake. It is 3 miles wide, holding millions and millions of gallons of water. But the absolute deepest point of the lake is exactly 100 feet deep. The formula insists that the pressure on a 1-inch square at the bottom of that massive lake is also exactly 43.3 psi. How can millions of gallons of water not exert more pressure than a tiny 1-inch pipe?
It is entirely about vectors. Pressure is a measure of force applied perpendicular to the surface of an object. In a liquid, gravity only pulls straight down. Think about a specific 1-inch square drawn in the mud at the very bottom of that 3-mile-wide lake. Gravity is pulling the entire mass of the lake downward.
Right.
But the water sitting to the left of our 1-inch square is being pulled down onto the mud to the left. The water to the right is pulled down onto the mud to the right.
The lateral forces the water pushing sideways against other water, cancel each other out, or are supported by the sloping walls of the lake basin itself.
Exactly. The only water that is physically pushing down on our specific 1-inch square is the exact column of water stacked perfectly vertically above it. And that column is exactly 1 inch wide, 1 inch deep, and 100 feet tall.
Which is physically identical to the column of water inside your PVC pipe.
Yes. The millions of surrounding gallons do not add downward vector force to that specific square inch. Therefore, the pressure is identical. Hydrostatics cares only about depth, never about width.
This is why skyscrapers have dedicated water tanks placed every 10 or 15 floors. They use the vertical height to generate head pressure to feed the plumbing for the floors immediately below them, leveraging gravity instead of relying on massive, continuous electric pumps pushing from the basement.
That perfectly encapsulates hydrostatics. But, as we mentioned in the opening of this deep dive, water rarely stays static when a safety professional gets involved. When a fire breaks out, valves open, and massive amounts of liquid are suddenly forced into motion.
Which brings us to hydraulics and the critical reality of friction.
When water is static, the pressure is stable. But the moment it begins flowing through a pipe, it interacts with the physical world. The water molecules rub against the microscopic imperfections on the interior walls of the iron or copper pipe. This creates friction.
And friction creates heat, which is a loss of energy from the system.
As the water travels further down the pipe, spending energy fighting friction, the pressure drops. And crucially, the faster the water moves, the more violent the friction becomes.
Why does speed change the friction so dramatically?
It alters the nature of the fluid flow. At very low speeds, water exhibits laminar flow. The molecules travel in smooth, parallel layers, sliding easily past one another. The friction is minimal. But as the velocity increases, the flow becomes turbulent. The water molecules start tumbling, swirling into chaotic eddy currents, crashing into the walls and into each other.
Wow.
This turbulence eats massive amounts of energy, causing the pressure to plummet exponentially.
Which introduces the final major mathematical relationship we need to master, the flow rate pressure relationship. The sources provide the foundational equation derived from Bernoulli's principles applied to pipe flow. Q1 over Q2 equals the square root of P1 over P2.
This states that the ratio of two different volumetric flow rates is equal to the square root of the ratio of their corresponding pressures.
It's the square root that defines the exponential nature of friction. If I have a fire hose delivering 100 gallons per minute at a pressure of 50 psi, and the fire chief yells that we need twice as much water to knock down the flames, we need 200 gallons per minute. My instinct is just to dial the pump up to twice the pressure, 100 psi.
But if you double the pressure, you will not double the flow. Because of the square root relationship, the benefit of added pressure suffers from diminishing returns. The turbulence is fighting you. To double the flow rate, you actually have to quadruple the pressure. To get 200 GPM, you would have to crank the pump all the way to 200 psi.
Which the pump might not be physically capable of doing, or the hoses might burst. The physics are unyielding. And this brings us back to the warehouse fire scenario we opened with. The sources provide a highly specific variation of this relationship used by fire protection engineers.
The Hazen-Williams friction model.
Right. Instead of using a simple square root, which is mathematically an exponent of 0.5, the Hazen-Williams formula adjusts for the specific frictional realities of commercial pipe materials by using an exponent of 0.54. Let's look at the practice problem provided for a municipal flow test, because this is the exact type of multi-step problem that separates passing from failing on the ASP exam.
The scenario is this. We are testing a fire hydrant system. Before we open any valves, we attach a gauge. The static pressure of the system S is 70 psi.
The potential energy of the water tower up the street.
Then, we fully open a hydrant down the block and let the water flow. We measure this initial flow rate, Q1, at 5,700 gallons per minute. While the water is rushing out, we check our gauge again. The pressure has dropped significantly. This is our residual pressure, R1, and it reads 36 psi.
Okay, so the act of moving 5 and 700 gallons per minute caused the system pressure to drop from 70 down to 36. That is a pressure drop of 34 psi sacrificed entirely to pipe friction.
Now, the exam question asks, what is the absolute maximum flow available from this specific hydrant? And it provides a regulatory definition. Maximum flow is achieved when the residual pressure drops to exactly 20 psi. We will call this target minimum pressure R2.
Before we run the math, we have to understand the why. Why do fire codes arbitrarily draw the line at 20 psi? If the building is burning down, Why wouldn't we just open the valves wider and suck the system down to 0 psi to get every drop of water?
Because of the consequences to the municipal infrastructure. A city's water system is a vast, interconnected web of underground pipes. If you draw the pressure down below 20 psi at a hydrant, you run the risk of creating negative pressure of vacuum in the surrounding mains.
And underground pipes are never perfectly watertight.
Exactly. They have microscopic cracks and leaky joints. If you create a vacuum inside a city water main, the pipe will actively suck in the surrounding groundwater. That groundwater might be contaminated with fertilizers, industrial runoff, or raw sewage from a nearby broken sewer line.
That's horrifying.
You would be pulling raw sewage directly into the clean drinking water supply for the entire neighborhood. The 20 psi limit is a structural safety buffer to ensure the pipes always maintain positive outward pressure, preventing contamination.
So 20 psi is the absolute floor. Our job is to calculate the theoretical flow rate, Q2, when the friction is so violent that it drags the system pressure down from the static 70 all the way to the 20 psi floor.
We use the Hazen-Williams adaptation. Q1 over the quantity S minus R1 to the power of 0.54 equals Q2 over the quantity S minus R2 to the power of 0.54.
We won't narrate every calculator keystroke here, but let's look at the architecture of the algebra. We know Q1 is 5,700. The denominator on the left is our initial pressure drop. The static 70 minus the residual 36, which is 24. We raise 34 to the power of 0.54.
And on the right side of the equation, we have our unknown maximum flow, Q2, sitting over our maximum allowable pressure drop. The static 70 minus the floor of 20, which is 50, we raise 50 to the power of 0.54.
Through cross-multiplication, we essentially isolate Q2. We find the ratio between our two pressure drops, the 50 divided by the 34, raise that ratio to the 0.54 exponent, and multiply it by our original 5,700 flow.
And when the math settles, the result is approximately 7,011 gallons per minute. That is the physical limit of the system. If you try to pull 7,012 gallons, you break the 20 psi barrier and risk contaminating the city water.
And this math is the invisible architecture that governs every commercial building. Let's return to the warehouse fire from the hook. The building burned down because someone changed the inventory.
The original sprinkler system might have been hydraulically calculated to suppress a fire on wooden pallets, requiring, say, 1,450 GPM at a residual pressure of 30 psi.
But the manager moved in high-density plastics and stacked them 10 feet higher. The fire load increased. The safety engineer looks at the new hazard and realizes that 1,450 GPMs won't even dent a plastic fire. They need 2,000 GPM delivered over the exact same area.
Because the pipes are already built into the ceiling, the physical area, A, cannot change. The only way to increase the volumetric flow, Q, from 1450 to 2000 is to force the water to move faster, increase the velocity, V.
But pushing water faster creates exponentially more turbulent friction.
By using the flow pressure relationship, the engineer calculates that to push that extra 550 gallons per minute through the existing pipe network, the pressure required at the fire pump doesn't just go up a little, it skyrockets. If the building's fire pump is physically incapable of generating that new massive pressure requirement, the sprinkler system is functionally useless for the new hazard. The water will just dribble out.
The math dictates the operational reality. If the pump can't hit the pressure, the warehouse cannot legally or safely store the plastic. It's that simple.
Which is why the ASP exam focuses so heavily on these concepts. You aren't just an administrator filling out safety checklists, you are auditing the physical limits of the infrastructure.
We have covered an immense expanse of physics today. From the foundational conservation of math and Q equals VA, understanding the seesaw between area and velocity.
We analyzed the invisible pressure dynamics inside a duct, breaking down total pressure into the static bursting force and the kinetic velocity force, and visualized how displacing water in a U-tube gives us the inches of water gauge measurement.
We unpacked the derivation of the 4005 constant from Bernoulli's principle and warned against the trap of using it when altitude or temperature destroy the assumption of standard air.
We tackled dilution ventilation, pulling apart the BEAST equation to balance the hazard generator of specific gravity and evaporation rates against the safety threshold of molecular weight and exposure limits. And we spent crucial time defining the K factor, the engineering safety net designed to combat the chaotic reality of dead zones and short-circuiting airflow.
We respected the inverse square law in local exhaust ventilation, realizing that moving a hood just slightly further away from a toxic source isn't a linear penalty. It requires an exponential explosion in fan power to maintain suction against the 360-degree sphere of influence.
And finally, we shifted to the heavy, dense reality of liquids. We proved that hydrostatic head pressure is dictated purely by vertical height, completely ignoring the volume of the tank due to the vertical vectors of gravity. And we ended with the turbulent friction of hydraulics, utilizing the Hazen-Williams formula to understand exactly why doubling your water flow requires quadrupling your pressure.
To you, the listener, doing the grueling work of studying for the ASP, this is a massive domain. But you are not just memorizing the position of variables on a page. You are learning the language of the physical world. You are learning how to look at a sheet metal duct or an iron pipe and see the chaotic, powerful forces of molecular friction and kinetic energy operating inside them. The exam tests your math, but the certification proves you have the capability to ensure that a worker isn't poisoned by a stagnant cloud of solvent, or that a warehouse doesn't burn to the ground because of a misunderstood pressure drop. You are becoming the architect of the invisible safety net.
The formulas are just tools to execute the mission of keeping people alive. But I want to leave you with a final thought to ponder as you close your books today. We've spent this entire deep dive calculating fluid dynamics based on static, unchanging infrastructure. Fixed pipe diameters, constant fan speeds, rigid sheet metal. The math assumes the building is dumb. But as industrial architecture moves into the era of AI and integrated smart sensors, that assumption is breaking down. Imagine a ventilation system that doesn't just run at a constant Q. Imagine ductwork lined with responsive materials that dynamically alter their own internal geometry in real time. A duct that senses a sudden, massive chemical spill, a spike in the evaporation rate, and physically constricts its own cross-sectional area, A, acting like a muscular iris, to instantly multiply the capture velocity, V, at the exact point of the spill without requiring the fan to spin a single RPM faster. The rigid equations you learn today won't just be pencil and paper calculations. They're becoming the underlying nervous system for autonomous buildings that will literally adapt and breathe to protect the humans inside them.
An infrastructure that reacts to fluid dynamics in real time. That changes everything about how we design safety. Thank you for joining us on this incredibly deep dive into the physics of flow. Keep fighting through those practice problems. Keep questioning the hidden forces moving through the pipes above your head, and we will catch you on the next deep dive.